Hello all, welcome to this video on probability and distributions. Today I'll be talking about sum rule, product rule, Bayes theorem, summary statistics and independence. We think of probability theory as an extension to logical reasoning. Probabilistic modeling provides a principled foundation for designing machine learning methods. Once we have defined probability distributions corresponding to the uncertainties of the data and our problem, it turns out that there are only two fundamental rules, that is the sum rule and the product rule. The first rule, the sum rule, states that P of x is sigma y element of y, P of x comma y if y is discrete, and integral with the lower limit y, P of x comma y dy if y is continuous, where capital Y are the states of the target space of random variable y. This means that we sum out or integrate out the set of states y of random variable y. The sum rule is also known as the marginalization property. The sum rule relates the joint distribution to a marginal distribution. In general, when the joint distribution contains more than two random variables, the sum rule can be applied to any subset of random variables, resulting in a marginal distribution of potentially more than one random variable. More concretely, if x is x1 etc. xd transpose, we obtain the marginal p of xi, which is integral p of x1 etc. xd dxi by repeated application of the sum rule, where we integrate or sum out all random variables except xi, which is indicated by this, which reads all except I. The second rule, known as the product rule, relates the joint distribution to the conditional distribution via P of x y, which is written as P of x into P of y given x. The product rule can be interpreted as the fact that every joint distribution of two random variables can be factorized of two other distributions. The two factors are the marginal distribution of the first random variable P of x and the conditional distribution of second random variable given by the first, which is P of y given x. Since the ordering of random variables is arbitrary in P of x, y, the product rule also implies P of x comma y, which can be written as P of x given by into P of y. In machine learning and Bayesian statistics, we are often interested in making inferences of unobserved random variables, given that we have observed other random variables. Let us assume that we have some prior knowledge P of x about an unobserved random variable x and some relationship P of y given x between x and a second variable y, which we can observe. And if we observe y, we can use Bayes theorem to draw some conclusions about x given the observed values of y. Bayes theorem, also known as Bayes rule or Bayes law, is P of x given y, which is posterior, which is equal to P of y given x, which is likelihood, into P of x, which is prior, divided by P of y, which is the evidence. This is a direct consequence of the product rule we discussed before. P of x comma y is P of x given y into P of y, and P of x y is P of y given x into P of x, so that P of x given y into P of y is P of y given x into P of x, which is given by P of x given y, which is written as P of y given x into P of x divided by P of y. The likelihood P of y given x describes how x and y are related, and in the case of discrete probability distributions, it is the probability of the data y if we were to know the latent variable x. Note that likelihood is not a distribution in x, but only in y. We call P of y given x either the likelihood of x given y or the probability of y given x, but never the likelihood of y. The posterior p of x given y is the quantity of interest in Bayesian statistics because it expresses exactly what we are interested in. That is, what we know about x after having observed y. The quantity p of y, which is integral of p of y given x into p of x dx, which can be written as expectation of p of y given x of a random variable x, which is the marginal likelihood or evidence. Bayes' theorem allows us to invert the relationship between x and y given by the likelihood. Therefore, Bayes' theorem is sometimes called the probabilistic inverse. Now we look into summary statistics and independence. We are often interested in summarizing sets of random variables and comparing pairs of random variables. A statistic of a random variable is a deterministic function of that random variable. The summary statistics of a distribution provide one useful view of how a random variable behaves and, as the name suggests, provide numbers that summarize and characterize the distribution. We now describe mean and variance, which are the two well-known summary statistics. Then we'll discuss the two ways to compare a pair of random variables. The first one is how to say that two random variables are independent, and the second is how to compute an inner product between them. Now let us look into means and covariances. Both are useful to describe properties of probability distributions, which is the expected values and the spread. The concept of expected value is central to machine learning, and the foundational concepts of probability itself can be derived from this expected value. The expected value of a function g mapped from R to R of a univariate continuous random variable x, p of x, is given by expectation of g of x of a random variable x, which is integral with the lower limit x, g of x, p of x dx. Correspondingly, the expected value of a function g of a discrete random variable x, p of x, is given by expectation of g of x of a random variable x, which is sigma x element of x, g of x into p of x, where x is the set of possible outcomes, which is the target space of the random variable x. Now, the mean of a random variable x with states x belonging to the d-dimension space is an average and is defined as expectation of x of a random variable x given by ex1 of x1, etc., exd of xd, all of them belonging to the d-dimension space, where expectation of xd of a random variable xd is given by integral with the lower limit x, xd, p of xd, dxd, if x is a continuous random variable, and sigma xi element of x, xi into p of xd equal to xi, if x is a discrete random variable, for the case where d varies from 1 to d, where the subscript d indicates the corresponding dimension of x. The integral and sum are over the states x of the target space of random variable x. In one dimension, there are two other intuitive notions of average, which are the median and mode. Median is the middle value if we sort the values, that is, 50% of the values are greater than the median and 50% are smaller than the median. This idea can be generalized to continuous values by considering the value where the cumulative distribution function is 0.5. For distributions which are asymmetric or have long tails, the median provides an estimate of a typical value that is closer to human intuition than the mean value. Furthermore, the median is more robust to outliers than the mean. The generalization of median to higher dimensions is non-trivial, as there is no obvious way to sort in more than one dimension. The mode is the most frequently occurring value. For a discrete random variable, the mode is defined as the value of x having the highest frequency of occurrence. For a continuous random variable, the mode is defined as a peak in the density p of x. A particular density p of x may have more than one mode, and furthermore, there may be very large number of modes in high dimensional distributions. Therefore, finding all the modes of a distribution can be computationally challenging. Now let us consider a two-dimensional distribution, which is a Gaussian distribution, which is given by n of its mean and the variance, which is sigma square. Also shown here is its corresponding marginal distribution in each dimension. We can see that the distribution is bimodal, that is, it has two modes, but one of the marginal distribution is unimodal, means it has one mode. The horizontal bimodal univariate distribution illustrates that mean and median can be different from each other, while it is tempting to define the two-dimensional median to be the concatenation of the medians in each dimension. The fact that we cannot define an ordering of two-dimensional points makes this difficult. When we say cannot define an ordering, we mean that there is more than one way to define the relation less than, so that 3, 0 less than 2, 3 from the figure. Now let us look into covariance. Covariance between two univariate random variables x, y, which are real numbers, is given by the expected product of their deviations from their respective means, which is covariance of x, y of random variables x, y given by expectation of x minus expectation of x of a random variable x into y minus expectation of y of a random variable y, the whole of a random variable x, y. By using the linearity of expectations, the expression can be rewritten as the expected value of the product minus product of the expected value, which means covariance of x, y can be written as expectation of x, y minus expectation of x into expectation of y. The covariance of a variable with itself, that is covariance of x, x, is called the variance and is denoted by Vx of a random variable x. The square root of variance is called the standard deviation given by sigma of x. The notion of covariance can be generalized in multivariate random variable also. If we consider two multivariate random variables x and y with states x belonging to d-dimension space and y belonging to e-dimension space, the covariance between x and y is defined by covariance of x, y written as expectation of x, y transpose minus expectation of x into expectation of y transpose, which can be written as covariance of y, x, the whole transpose, which belongs to D cross E. Now the variance of a random variable x with states x belonging to d-dimension space and a mean vector mu belonging to the same space is defined as variance of x of a random variable x written as covariance of x, x of a random variable x written as expectation of x minus mu into x minus mu transpose of a random variable x, which is expanded as expectation of x, x transpose of a random variable x minus expectation of x of a random variable of x into expectation of x transpose of a random variable x, which gives us this matrix beginning from covariance of x1, x1 to covariance of xd, xd. This d by d matrix is the covariance matrix of the multivariate random variable x. Covariance matrix is symmetric and positive definite and tells us something about the spread of the data. On its diagonal, the covariance matrix contains the variance of the marginals. p of xi given by integral of p of x1 etc. xd dxi, where this denotes all variables but I. The off-diagonal entries are the cross covariance terms, covariance of xi comma xj for I j equal to 1 to d and I not equal to j. When we want to compare the covariance between different pairs of random variables, it turns out that variance of each random variable affects the value of the covariance. The normalized version of covariance is called the correlation. Correlation between two random variables x, y is given by correlation of x comma y, which is written as covariance of x comma y by root of variance of x into variance of y, whose value will be in the range -1 to 1. Correlation matrix is the covariance matrix of standardized random variables x by sigma of x. The covariance and correlation indicate how two random variables are related. For example, in case of a positive correlation, it means that when x grows, y is also expected to grow. In negative correlation, when x increases, y will decrease. Now we look into empirical means and covariances. Consider a random variable x. There are two conceptual steps to go from population statistics to the realization of empirical statistics. First, we use the fact that we have a finite data set of size n to construct an empirical statistic that is a function of a finite number of identical random variables x1 to xn. Second, we observe the data. That is, we look at the realization x1 etc. xn of each of the random variables and apply the empirical statistic. Specifically for the mean, given a particular data set, we can obtain an estimate of the mean, which is called the empirical mean or sample mean. The same holds for empirical covariance. The empirical mean vector is the arithmetic average of the observations of each variable, and it is defined as x bar given by 1 by n into sigma n is equal to 1 to n xn, where xn belongs to d-dimension space. Similarly, empirical covariance matrix, which is D cross D matrix, sigma is given by 1 by n into sigma n is equal to 1 to n xn minus x bar into xn minus x bar, the whole transpose. To compute the statistics for a particular data set, we would use the realization, that is the observations x1 to xn, and use the two equations we mentioned before. Empirical covariance matrices are symmetric and positive semi-definite. We now focus on a single random variable x and use the preceding empirical formulas to derive three possible expressions for the variance. Now, the standard deviation or definition of variance corresponding to the definition of covariance is the expectation of the squared deviation of a random variable x from its expected value mu. That is, variance of x of a random variable x given by expectation of x minus mu the whole square of a random variable x. The variance as expressed is the mean of a new random variable z, which is x minus mu the whole square. While estimating the variance empirically, we need to resort to a two-pass algorithm. One pass through the data to calculate the mean mu, and the second pass using this estimate mu cap to calculate the variance. It turns out that we can avoid two passes by rearranging the terms into a form called the row score formula for variance, given by variance of x of a random variable x written as expectation of x square of a random variable x minus expectation of x of a random variable x the whole square. This can be also said as the mean of square minus the square of the mean. It can be calculated empirically in one pass through data, since we can accumulate xi and xi square simultaneously, where xi is the ith observation. Unfortunately, if implemented in this way, it can be numerically unstable. The row score version of the variance can be useful in machine learning. That is the case when deriving the bias variance decomposition. A third way to understand variance is that it is a sum of pairwise differences between all pairs of observations. Consider a sample x1, etc., xn of realizations of random variable x, and we compute the square difference between pairs of random variable xi and xj. By expanding the square, we can show that sum of n square pairs differences is the empirical variance of the observations. 1 by n square sigma ij equal to 1 to n xi minus xj the whole square, written as 2 into 1 by n sigma I is equal to 1 to n xi square minus 1 by n sigma I is equal to 1 to n xi the whole squared. Now this means that we can express the sum of pairwise distances, of which there are n square of them, as the sum of deviations from the mean, of which there are n. Now we look into sums and transformations of random variables. Consider two random variables x, y with states x, y belonging to d-dimension space. Then e of x plus y can be written as e of x plus e of y. E of x minus y can be written as e of x minus e of y. V of x plus y can be written as v of x plus v of y, plus covariance of x comma y plus covariance of y comma x. V of x minus y can be written as v of x plus v of y minus covariance of x comma y minus covariance of y comma x. Now they exhibit some useful properties when it comes to affine transformation of random variables. Consider a random variable x with mean mu and covariance matrix sigma and a deterministic affine transformation y is equal to ax plus b of x. Then y is itself a random variable whose mean vector and covariance matrix are given by expectation of y of a random variable y, written as expectation of ax plus b of a random variable x, rewritten as a into expectation of x of a random variable x plus b. Again, on substituting, we get a mu plus b. Similarly, variance of y of a random variable y, written as variance of ax plus b of a random variable x, written as variance of ax of a random variable x, which can be written as a into variance of x of a random variable x into a transpose, which gives us a sigma a transpose. Furthermore, covariance of x comma y can be written as expectation of x into ax plus b the whole transpose minus expectation of x into expectation of ax plus b transpose. On substitution, we get it as sigma a transpose, where sigma is given by expectation of x transpose minus mu transpose, which is the covariance of x. Now we look into statistical independence. Two random variables x, y are statistically independent if and only if p of x comma y can be written as p of x into p of y. Intuitively, two random variables x and y are independent if the value of y, once known, does not add any additional information about x and vice versa. If x, y are statistically independent, then p of y given x will be p of y, p of x given y will be p of x, variance of x plus y of random variables x and y will be variance of x of a random variable x plus variance of y of a random variable y. Covariance of x, y of random variables x, y will be 0. The last point may not hold in converse, that is, two random variables can have covariance 0 but are not statistically independent. To understand why, recall that covariance measures only linear dependence. Therefore, random variables that are non-linearly dependent could have covariance as 0. Let us consider a random variable x with 0 mean. Expectation of x of a random variable x is 0, and also expectation of x cube of a random variable x is 0. Let y is equal to x square, which means y is dependent on x, and consider the covariance between x and y. We will see that covariance of x comma y, which can be written as expectation of xy minus expectation of x into expectation of y, which is expectation of x cube will be 0. Two random variables x and y are conditionally independent given z if and only if p of x comma y given as z is p of x given z into p of y given as z for all z belonging to capital Z, where capital Z is a set of states of random variable z. We write it in this notation to show that x is conditionally independent of y given z. This definition requires that the relation we just mentioned before must hold true for every value of z. The interpretation can be understood as, given knowledge about z, the distribution of x and y factorize. Independence can be cast as a special case of conditional independence if we write it in this form. By using the product rule of probability, we can expand the LHS as p of x comma y given as z, which is p of x given y z into p of y given z. By comparing the RHS of two equations, we see that p of y given as z is appearing in both. On cancelling, we get p of x given y comma z will be p of x given z. Now we look into inner products of random variables. If we have two uncorrelated random variables x and y, then variance of x plus y will be variance of x plus variance of y. Since variances are measured in squared units, this looks very much like the Pythagorean theorem for right angles, where c square is equal to a square plus b square. Now we'll see whether we can find a geometric interpretation of the variance relation of uncorrelated random variables. Random variables can be considered as vectors in a vector space, and we can define inner products to obtain geometric properties of random variables. So if we define inner product of x comma y as covariance of x comma y, for 0 mean random variables x and y, we obtain an inner product. We see that covariance is symmetric, positive definite, and linear in either argument. The length of the random variable is given by root of covariance of x comma x, which is root of variance of x, which is the standard deviation of x. The longer the random variable, the more uncertain it is, and the random variable with length 0 is deterministic. If we look at the angle theta between two random variables x and y, we get cos theta given by inner product of x comma y by length of x into length of y, which is written as covariance of x comma y by root of variance of x into variance of y, which is the correlation between the two random variables. This means we can think of correlation as the cosine of angle between the two random variables when we consider them geometrically. We know from the definition that when x is perpendicular to y, it means the inner product will be 0. So in our case, this means x and y are orthogonal if and only if covariance of x comma y is 0. That is, when they are uncorrelated. Now this is illustrated in this figure here. If random variables x and y are uncorrelated, they are orthogonal vectors in a corresponding vector space, and the Pythagorean theorem applies here. That's all for now. Thank you for watching.